think we can start. Good morning, everybody. I'm Etienne de Klerk, and I am going to give a two-part tutorial today about conic linear optimization. Specific focus on the general problem of moments. So this is nothing new. It's all classical. So this is primarily intended as something for the ESRs and for those who are interested to understand how the linear optimization duality changes if we move from finite dimensional spaces to infinite dimensional spaces, because this is precisely what we need if we study the duality of the general problem of moments. Just a couple of practical comments. I cannot see everything in the chat due to my setup, but my ESR Felix Kirchner will help me today, will assist me. So Felix, I just ask that if there is, thank you, there's Felix, if there is anything crucial that I'm missing, or if you cannot see anything, please interrupt me. And for the rest, it's very hard to have a discussion with so many people during online lecture. So I would ask you, please type your comments in the chat box. And I would be very happy if we make it a group effort. So if you see a question in the chat box that you know how to answer, please don't be shy. Also, I'm absolutely not an expert in all the things I'm going to talk about, so I would appreciate any help I can get. Okay, so let's just try to get going and see how it goes. So in this first part, I want to speak about duality theory, and I'm going to base my lecture on this book by Alexander Barvinok. It's called Course in Convexity, and it's really a wonderful resource for people who want to understand finer details of convex analysis, and not only in the Euclidean space, but in more general topological vector spaces. So I can really recommend this extremely highly if you want to have a deeper understanding of duality theory. So basically what we will speak about in this first hour is linear programming or linear optimization over cones. So this is called conic linear optimization. And then of course the fundamental theorems associated with this kind of duality is the weak and strong duality theorems. Now, I'm sure everybody here has at least had duality theory for linear optimization. So this is an example in the Euclidean space. So mostly we're going to see what has to change for us to analyze these linear optimization duality results in more general spaces. And that will allow us to study the duality of the general problem of moments. Okay, so let's get going. It's going to be a little bit dry because we will have to speak a bit about topological vector spaces, but just bear with me, there is a point to all of this. So, so we're just going to consider a very general situation of two real vector spaces, E and F, assumptions. And we're going to define something called the bilinear form on these two vector spaces. So the bilinear form takes two arguments. The first argument is from the vector space E, second is from F, and we call such a function a bilinear form if it's the case that if we fix the first argument, so we fix it to some E and E, so we fix E to some vector in the vector space E, and we look at this function that maps F to this the function evaluated at E and F, and this is a linear function of F. Okay, and similarly, so if we fix some F from the space F, and just look at the function that maps E to this, then this should be a linear function in E. So if this is true, then it's called a bilinear form. So if we fix one of the two arguments, it becomes a linear function. Okay, and then there's a second concept of a bilinear form being non-degenerate. So and it's non-degenerate if the following implications hold for this bilinear form. So basically, if we find that this bilinear form evaluated at E and F is zero for all E and E for a given F, then this given F must be equal to 0. Okay, and similarly, if we find that for a given E, this thing evaluates to 0 for all F and F, then this E has to be 0. So yeah, so this is in fact a generalization you will understand of the concept of the inner product. So for example, if the spaces E and F are the same space and the space is the inner product space, then this inner product is an example of a duality. So this bilinear form is called a duality. It's also called the pairing of the vector spaces E and F in the literature. So I might sometimes speak about pairing for this bilinear function because duality has many meanings. But in the book of Barbanov, it consistently speaks about the duality, but pairing is also quite common. And in the case, remember always that the special case of a duality is a inner product. These spaces are the same and an inner product space. Okay, so indeed, so if we just look at a few examples, then it's just what I said. You can verify for yourself very easily that our familiar inner products are dualities. So if the space E and F is a Euclidean space, and this duality of this bilinear function is given by the usual inner product, but obviously this is bilinear. If we fix the eta coordinates of the vector y, then it's linear in the coordinates of x. Just note Barbanov likes to use the Greek letters as coordinates. So x has coordinates x psi I to psi d. I has coordinates eta 1 to eta d. So it's obviously a bilinear form, and it's a very easy exercise to show that it's non-degenerate. So it's indeed a duality. And this is a very simple example. So similarly, I think many of us are interested in semi-different programming. So we like optimizing over symmetric matrices, and then we have this familiar inner product on the space of symmetric matrices. So if the two vector spaces we consider are both symmetric matrices, then we can define this inner product as Euclidean inner product. So where these are just the ijth elements of the matrices A and B respectively. So this is really just the Euclidean inner product for the matrices. And one can also write it, as you may know, in terms of the trace, the sum of diagonal elements of A times B. And then for this reason, it's also called the trace inner product sometimes. So again, this is an example of a duality. And a good warming exercise, a good warming up exercise is for you to show that it's indeed a non-degenerate bilinear form. And then important for us if we're going to study the general problem of moments is this less trivial example or less simple example where the spaces E and F are actually different spaces. So basically we have one space of continuous functions, and we're going to keep it simple in most of the lectures. Let's just fix the continuous functions on the interval 0, 1. So these are just univariate continuous functions on the interval 0, 1. And then we can also have a second space, which is the space of signed Borel measures on 0, 1. And then we have this interesting duality or pairing of the function f with the measure mu, which is just given by the integral of the function with respect to the measure. Okay, so this is a good warming exercise for you now to show that this is indeed a duality. So the bilinear property is quite easy, but for the non-degeneracy, you might have to think slightly, but it's also relatively straightforward. So this is a good exercise to start with. Convince yourself that this is a duality between the space of continuous functions on 0, 1 and the signed Borel measures on 0, 1. Okay, so something else that we have in this linear optimization problems are linear constraints. From Ax is equal to B usually for some linear operator A. So, and then we also usually have a associate adjoint operator. And also this concept can be generalized to a more general concept of a dual or adjoint linear operator as follows. So here we have now a little bit of a complicated setup. Let's go through it. We have two dualities, a duality 1 and a duality 2. And duality 1 is defined on the Cartesian product of the vector spaces E1, F1, similar for duality 2. And basically we also have now a linear transformation from E1 to E2, and the second linear transformation A star from F2 to F1. Now, by definition, A star is called the dual or the adjoint operator of the linear operator A if this identity holds. for all E from the vector space E1 and F from the vector space F2. Okay, let's just at least do a reality check here. So this duality number 2 takes its arguments from E2 and F2 respectively. So AE indeed is something in the vector space E2, okay, and F is in this vector space F2. So at least it makes sense. We can evaluate this. This is a real number, and similarly we evaluate this. And if it's the same for all possible vectors from these two spaces, we say A star is the dual operator or the adjoint operator of the linear operator A. Okay, so again, this is a generalization of something that everybody knows, namely the more familiar adjoint that's associated with an inner product. So for example, if we just take the two spaces E1 and F1 equal to Rn, and the two spaces E2 and F2 equal to Rm, and we take the first duality to be the Euclidean inner product on Rn, and the second duality to be the Euclidean inner product on Rm, then basically if we view the matrix A as a linear transformation in the usual sense, so A maps a vector in Rn by just multiplying A by the vector, and you get something in Rm. Then the linear operator associated with the transpose of this matrix is going to be its dual operator. Okay, so this is just something to make this abstract definition a bit more concrete. So it's a good exercise for you. Just verify that in the special cases where these spaces are Euclidean and these are also equal and Euclidean, and then we find the familiar fact that the transpose of the matrix A is the dual adjoint operator with respect to the Euclidean inner product. Okay, so the other ingredient in conic linear optimization, apart from these constraints Ax equals to B, we of course also have a cone over which we optimize. So we usually have an affine space defined by Ax equals to B, and this intersects some cone, and this is our feasible set. So now let's just look a little bit at some concept called partial ordering by a cone. And then we again have some general vector space, and we have some convex cone inside this vector space. Let's just remember a cone is a convex set we know, and a cone, of course, is just a convex cone is just a convex set that's closed under non-negative scalar multiplication, which is defined because we are in space. Okay, so now the cone defines a partial order on the vector space by saying an element X in the vector space is smaller or equal to an element Y in the vector space if and only if Y minus X belongs to the cone. Okay, so this is a partial ordering in the mathematical sense. So you can actually prove this to yourself. It satisfies all the properties like reflexivity and transitivity of a partial order. So this is a nice exercise. And just to notice a bit of the notation, okay, so we can also put K as subscript in the inequality just to remind ourselves which cone we are talking about. Because yes, in general, we might be speaking of several cones at the same time, so we might just put the K to remind ourselves which cone we have in mind. But if there's no confusion possible, we just write it like this. And we might also switch the inequality, excuse me. So instead of writing X small equal Y, we might write Y greater equal X. So we just understand it in that way. And also in the literature, we quite often see the partial order sign is this. So I think this is actually the more proper notation, but Radinov uses the smaller equal notation. Okay, so in particular, I just want to show it one thing. So basically, if I want to say Y belongs to the cone, so just look at X is equal to 0. So if we read this from right to left, we see Y greater equal 0 is the same as Y belonging to the cone. So we will use that a lot. So greater equal 0 just means it belongs to the cone. Okay, so let's just again look at our examples from before. So how does this look like for the cones that we all know? So first of all, we have in the space, the Euclidean space, we have the familiar cone, which is the non-negative orthant. So the vectors of length d with non-negative components. Yeah, so then basically we write x is small equal y, if and only if y minus x is component y is non-negative, which is of course the same as saying it belongs to this non-negative orthant. Okay, for this also semi-definite matrices, so now the vector space is the space of symmetric matrices, and the cone of positive semi-definite matrices consists of the symmetric matrices which are positive semi-definite, and we write the matrix X is small equal to matrix Y if and only if Y minus X is positive semi-definite. Okay, so again, greater equals 0 corresponds to positive semi-definite here. Greater equals 0 corresponds to belonging to the non-negative orthant. Okay, so for the general problem of moments, we are interested in these more exotic spaces of the Sine-Borel measures, and the cone is associated with the cone of non-negative measures. So we say the measure mu is small equal to measure nu if and only if nu minus mu is a non-negative measure. Okay, so just for those who are not really comfortable with this Borel measure, so a non-negative measure simply means that if you integrate any non-negative function with respect to this measure, that the answer will be a non-negative number. Okay, so this is if you don't have much background in theory like myself, then it's nothing very mysterious. You can just see it as that way. Okay, so also for the space of continuous functions, we have an associated cone, namely the non-negative functions. So obviously, you know, this is a cone again because the function is multiplied, the non-negative function is multiplied by a non-negative scalar, it remains non-negative, and you can take the sums of non-negative functions to get another non-negative function. So it's clearly a convex cone. And we write the function f1 is small equal to the function f2 if and only if the function f2 minus f1 is non-negative on the interval 0, 1. Okay, so we have these natural cones associated with the measures, the non-negative measures, and with the continuous functions, the non-negative functions. Good. So now you also know we had this idea about the dual cone. So if we have an inner cone and we have an inner product space, then we have a dual cone living in the same space. I think everybody has had this at some point. But now again, we are going to generalize this a bit by working with different spaces. So instead of having an inner product, we have a more general duality between two vector spaces E and F. And then, so we have a convex cone, K, that belongs to E. And then the so-called dual cone, K star, is a convex cone that belongs to the vector space F, with the property that consists of all the F's that have non-negative duality. If you evaluate the duality F together with any E from K, the result is a non-negative number. Okay, so you will recognize this. Looks extremely familiar to the usual definition of a dual cone using the inner product. So again, in the special case where the duality is an inner product and the spaces are the same, then this is just the definition that we all know of a dual convex cone. Yeah, so this is what I've just said. So if we have a non-negative orthant, for example, two spaces being the same, then the non-negative orthant is its own dual. We call it self-dual with respect to the Euclidean inner product. So if these spaces are the Euclidean space and the duality is in fact the Euclidean inner product, then it's just its own dual. So we all know this. You might also know this for the positive semi-definite matrices. If we have work in the space of matrices, both E and F are that, and the duality is the inner product, then its K is equal to its own dual. So the cone of positive semi-definite matrices is self-dual for the Euclidean trace inner product. Okay, so now finally we are almost in the position where we can state our linear optimization problem over cones, and we have quite a complicated setup. So I just want to I ask you to bear with me, and we just go through all the details. So we have two dualities, as before, 1 and 2. Duality 1 takes its arguments in vector spaces E1 and F1. Duality 2 takes its arguments in vector space E2 and F2. So we have convex cones, convex cone K1 in the vector space E1, convex cone K2 in the vector space E2, and then we define the dual cones of these K1 and K2 as before in terms of the dualities. Then we just have to understand that K1 star will be in the space F1, and K2 star will be in the space F2. And then we're not done yet. So for the linear constraints in linear programming, we need an operator A. So this our operator will map the vector space E1 to E2, and it will have an adjoint operator as defined before. So just remember, this is the general definition of adjoint. And just to help you, whenever we are dealing with adjoints, so you see the point is we have one duality here and a second duality here. And just to remember how this definition works, basically we can move A to the other side, and then it becomes A star, and also just the duality has to change to the correct duality. So if the dualities are the same and the same inner product, then the adjoint works as follows: you just move the A to the front of the L, and it becomes the adjoint. So just to help us remember how the adjoint operator works. Okay, so I would just like to just have a quick diagram about our setup, because it is actually quite complicated. So I just want to ask Felix, can you see the writing?
Yes, all nice and clear.
Try to get rid of the. Yes, that looks better. So this is basically our setup. If we just make a small diagram of it, so we have vector spaces E1, E2, F1, and F2. So each quadrant here is a vector space. Then we have this linear operator A mapping the space E1 to the space E2, and the adjoint will map F2 to F1 according to the definitions. And then we also have cones. We have a cone K1 in the space E1, K2 in the space E2, and then the respective dual cones. So the dual cone of K1 is K1 star, and this will live in the space F1. And the dual cone of K2 is K2 star. It will live in F2. And then we still have these two dualities to make our lives difficult. So we have duality number 1, duality number 2. And we just have to remember that, the first argument for duality 1 comes from the space E1. The second argument comes from the space F1. Similar here, the first argument comes from E2. The second argument comes from F2. And then it's when I have to deal with this general form, I really find it very useful to have this kind of scheme on hand, just because all this notation can drive you nuts. Okay, so just going back to the slides. Okay, so Felix, just to check, you see the slides again?
Yes, we do.
Thank you. Okay, so now that we have this general setup, we can write down the general form of a linear programming problem over the cone. Over cones. So here we have a minimization problem. We have an objective, duality of X and C, where X is from E1. And so this just means that C is from F1 by the definition of our duality 1. And then we have, at this time, we have constraints of the form AX minus B has to belong to the cone K2. So just I just bring the B to the other side and read it as greater equal to, and then it's easy to remember. I'm saying AX minus B belongs to the cone K2. and this means X belongs to the cone K1. So this is the primal problem. So we, okay, so then we have also associated with it a dual problem, just like you are familiar with in linear programming. But the only thing that makes these things difficult is that we have so many spaces flowing around in the different dualities, but conceptually it's just a straightforward generalization. So the optimal values, so the increment that the objective function takes on the feasible set is called gamma for the primal problem, and for the dual problem, the supreme value of the dual objective is called beta. And here, so the objective function is the duality evaluated at B and L. So if we just look at the duality 2, the first argument comes from E2, so B the vector in E2, and then L must be a vector in F2 as shown here, just for it to be defined. So then we have constraints, the adjoint times L minus C, C minus the adjoint times L must belong to the cone K1 star, and L must belong to the cone K2 star. Okay, so yeah, so you know it's a good sanity check for you to just simplify this, just to replace perhaps the dualities by inner products, and just to see that you recover the usual linear programming duals that you are used to in the special cases. But okay, so this is the most general situation for the conic linear optimization and its dual. Okay, so the interesting thing in duality theory is to compare these values gamma and beta. So there are essentially two types of theorems. We call them weak and strong duality theorems. And the weak duality theorems will say something like the gamma value is always greater equal to the beta value. And yeah, and the strong duality investigates when these gamma and beta values are actually equal. So this is the same as what you know. It's just the details are a little bit more complicated. Okay, so then you know the usual things. If X satisfies the primal constraints, we call it primal feasible, or Bilinear calls it the primal feasible plan. So okay, so just this, we are familiar with this concept that if X satisfies the primal constraints, is primal feasible. Similarly, if L is a dual variable. If you remember, if it satisfies the dual constraints, or a dual feasible or a dual feasible plan. And then we can also speak of optimal solutions or optimal plans. So the Bilinear calls the optimal solution optimal plans. Something else that you know is the difference between the primal objective, which was given by this duality evaluated at X and C, minus B and L, it's a duality gap. So it's defined as a duality gap. So again, the weak duality will tell us that this quantity is always non-negative at the primal feasible plans X and dual feasible plans L. Yeah, okay, so in particular at optimality, so the primal optimal value was gamma, the dual optimal value was beta, so at optimality this duality gap is actually gamma minus beta. Okay, so here is then the typical weak duality result that one can show. So if we have a primal feasible X and a dual feasible L, then the primal objective is going to be greater equal to the dual objective. Yeah, so these kind of things are the weak duality proofs are always elementary. So you do not need anything except the definitions to show this. So basically, it's just slightly more complicated than the usual weak duality proofs because we have some things, some different spaces and dualities floating around. But let's just try to convince ourselves that this is true. So I just switch back to the writing. So if we just try to consider how this looks like, then we have the primal objective at the primal feasible plan X minus the dual objective at the dual feasible plan and then we want to show, but we don't know if it's true, that this is greater equal to 0. And then, of course, we need to kind of try to remember where do all of these things live. So this L belongs to K2 star, and what we also know is from the primal feasible conditions, we have AX minus B belongs to the cone K2. This is one of the primal constraints. So then this just means that in terms of the duality relation, that this vector AX minus B that belongs to K2, if we take the right duality with L, and this right duality is a 2 duality, then this has to be greater equal 0. This is just by the definition of the dual cone. And then, yeah, so this then, just because this is a bilinear form, we just get this AX L2 is greater equal B L2. Okay, so basically this is already this part that we would like here. So then we just need to continue a little bit with this part here, and then so we also note that for the dual feasibility we have C minus A star L belongs in the dual cone of K1, and we also know X is in the cone K1. So then again, if we just evaluate the correct duality, this is in K1 star, this is in K1, the answer has to be non-negative. So if we take the duality between X and C minus A star L, and this is the 1 duality, this has to be greater equal 0. And then this just, of course, implies that XC in the 1 duality is greater equal X A star L in the 1 duality. And then we just know, again, what I said, the trick with the duality is we can move the A star to the front, it becomes A, and then the duality just changes. So this can be written as AX times L in the other duality 2. And this is the same thing as what we had there. So just putting it together, we get this is greater equal that. And that is exactly the weak duality theorem. Okay, so the point is, I mean, this is something just to remember in general. So the weak duality theorems are always just elementary in some sense. You only use the definitions. And the difficult part comes in the strong duality theorem. So in some sense, these weak duality theorems are no different in infinite dimensions or general spaces than what we are used to. Okay, so then there are some variations on the weak duality theorems. So you might remember from linear programming, or you might know more about it, is that, you know, the weak duality theorems imply or are in some sense equivalent to so-called complementarity conditions. And then these ones denoted by the heart, these are essentially complementarity conditions. So if X is primal feasible, L is dual feasible, and these so-called complementarity conditions hold, then X is optimal and L is optimal for the respective primal and dual problems, and there is no duality gap. So this is essentially just a way of restating the fact that, you know, if this is equal to that, then both X and L are optimal. So this is a nice exercise for you. Just this is just elementary. You can just prove this. This is this follows from the situation where these two things are actually equal. Then X and L are both optimal. And then there is another variation. If X is primal optimal, L is dual optimal, then and also the objective function values of the primal dual are equal, then the complementarity conditions must hold. Okay, again, this is straightforward. I think it's enough that we looked at the first proof, then you have the feeling for it. The others go just in the same way. I just show it to you that you can see that, you know, all the familiar things like complementarity conditions that you know, they're just generalized to this general setting. Okay, so very good. So now we have the weak duality, and it didn't really cost us much effort. So it was the only thing was that the notation is quite burdensome, so it's quite general, and it's hard to verify all the time that you are using the correct arguments for the dualities and you have the right the adjoint operator and so forth. But it was not really fundamentally difficult. Everything was just basically using definitions. But to prove a strong duality, so to give sufficient conditions of when gamma is equal to beta, we always rely on separating hyperplane theorems. So if you had a course in convex analysis or maybe nonlinear programming, you would have learned that strong duality theorems in general, they rely on separating hyperplane arguments. And in principle, for a suitable separating hyperplane to exist, we need some topological structure in the spaces that we work on. So we cannot have such general results as here for strong duality. So I ask you again to bear with me, because we will have to dive a little bit into the structure of topological vector spaces to understand which properties should the space have to have the correct separating hyperplanes leading to strong duality theory. Okay, so we have to speak a bit about topological spaces. So essentially, a topological space is just a vector space or a space where we have a concept of open sets. So basically, we are given a set X with a family of subsets. This family is denoted by F, and we call this family the open sets. And this family must have the property that the empty set and the full space are open sets. That intersections of finitely many open sets are open sets, and that unions, any unions of open sets are again open. The important thing here for us to understand is that if we have a topological space or topological spaces, this is enough to define continuity of functions on these spaces. Because we can have neighborhoods. For example, if I have a point in the space X, then any open set containing it is called a neighborhood of this point. And if we have neighborhoods, can define neighborhoods of points, we can define continuity. So let me just quickly explain this, because if you're not familiar with this is a slightly difficult. So let me just switch again to the writing. So this is really a simple but very important concept. For example, we have two topological spaces X and Y, and we have here a point in the space called X, and of course we have some function F that maps this to the space Y, and this is, so it just maps it to the point F of X. So now we can say that F is continuous at the point X if for any neighborhood of F of X in Y, so we just specify this neighborhood here, so this is some open set that contains F of X, then there exists a suitable neighborhood here of X, such that this neighborhood here is always mapped into that neighborhood there. So that if that says that if that is the case, then F is continuous at the point X, and it's of course is continuous on the whole space if it's continuous at every point X. So another way to say it is that if we look at the pre-images of open sets in Y, if these pre-images are always open sets in X, then the function is continuous. Okay, so that's the important thing. If we have a topological space, we have the concept of continuous functions. Okay, and now we add additional structure. So we have now not just a topological space, but also a vector space. And we also ask the additional properties of this vector space. So to merge it with the topological space. So we ask that if we have any vector in the vector space, then the singleton consisting of this vector is a closed set. So remember, the closed sets are always by definition just the complements of the open sets. And then we add the two basic functions associated with the vector space are continuous functions in the sense that I just discussed with you. So basically, if we look at a map, this takes two vectors x and y from
Etienne, can you hear me?
the vector space and adds them together. Of course, this is a fundamental operation of the vector space. This map must be continuous.
Oh, yeah.
And also the other fundamental operation of vector space is just to multiply a vector by a scalar. So we say also this function must be continuous, and then we arrive at the so-called topological vector space.
Can you hear me?
So then there is an interesting topology that is defined by duality. So we discussed dualities or pairings.
Etienne?
Okay, sorry, I see we cannot see your screen. Just 1 second. Can you see the screen?
Now we can.
Okay, sorry, I will repeat. I'm sorry. I just shout if it goes wrong, please. Okay, so basically, I'm talking about the topological vector spaces. So basically, so we have a vector space, and we require that there's a topology on this vector space with the properties that the singleton is a closed set, so it's a complement of an open set, and that these two functions are continuous. So the function that adds vectors together and the function that does scalar multiplication is also continuous. Okay, so basically we have a vector space which is also a topological vector space, and the topology has the property that singletons are closed sets and that these two types of maps are continuous maps. Okay, so now the interesting thing is that we can have a nice topological vector space defined by the weak topology of a duality. So it's just that the duality between vector spaces E and F defines a natural topology called the weak topology of the duality. How does this work? So remember, for the topological space we need open sets, right? So family of open sets. So we define a so-called basic open set, a U inside our vector space E, as given by these linear inequalities for some fixed vectors fi from F and some given numbers alpha I and beta I. So basically, these kind of linear boxes, for lack of a better term, these define our open sets. Okay, so and then we can define these are basic open sets, and then open sets are defined as unions of basic open sets, and that gives us a topology on the space E, and this is called the weak topology of a duality. Okay, and then so of course we can just switch the E and the F arguments, so in an obvious way, and we can also define open sets in F. So basically, the duality gives us a weak topology on both E and F. So the reason why this topology is interesting for us is basically it's rich enough to guarantee that there are plenty of continuous linear functionals on these spaces on the spaces E and F in this topology. So remember, for the continuity, we need the concept of open sets, and not every linear functional is continuous in infinite dimensional spaces. So there are even topological vector spaces where the zero functional is the only continuous linear functional. So I mean, if you are like me and you are used to working in finite dimensions, I mean, these things scare me. So if linear functions are no longer continuous, so we have to be very careful. So the nice thing about this weak topology of duality is that we have a good understanding of the existence of continuous linear functions. So in particular, if we just fix an F in F, and we look at this linear function here, then we are guaranteed that this is a continuous linear functional on E. And moreover, every continuous linear function on E may be rewritten in this way for suitable vector F from the vector space F. And the same way. So basically, if we for every fixed E in E, this is a continuous linear function on F, and every continuous linear function on F may be written in this way. So this is going to be extremely important for us because we want to define separating hyperplanes in terms of continuous linear functionals. And we have to know that our topology is rich enough that suitable continuous linear functionals exist. Okay, so let's just get back down to earth and try and understand a few special examples. So just fortunately, in the Euclidean space, everything is as it should be. So if we use the inner product as a topology, then we just get the usual familiar, the standard topology in Rn. We get the standard topology for the symmetric matrices. And for the other example that's important to us, so here we for the pairing of the continuous functions with the signed Borel measures, we get the so-called weak star topology. If you don't know what this is, I will get back to this later. It's just the important takeaway is we for all the examples that we study, we have a good understanding of what this weak topology of the duality looks like. Okay, so now finally we can talk about separating hyperplane theorems, and the only thing is that we don't yet have enough structure on our topological vector spaces. Well, I mean, we'll understand what I mean in a second. So we need something extra called local convexity. So the topological vector space is locally convex if every neighborhood of a given vector contains a convex neighborhood. So basically, if we have a neighborhood of a point, we have a smaller neighborhood inside, which is actually a convex set. So such a topological vector space is called locally convex. And but this is fine as long as we stick to the weak topology of duality. We have a locally convex topological vector space. So this is completely fine. So the separation theorem that we have is stated for these locally convex topological vector spaces, and it says the following. So if we have a locally convex topological vector space, and we have some set that belongs to it. Sorry, this is now not the linear operator A. It's just a closed convex set that belongs to our topological vector space. And if we have a point outside the set, then there exists a separating hyperplane that separates this point from the convex set. And you can describe this as in terms of the existence of a suitable continuous linear functional. So basically, there exists a continuous linear functional that maps F to R such that the function value at the point Q is greater than the function value for everything that lies in the set A. So so this is okay. So this is basically the thing that we're going to need to do the strong duality. So we need the existence of a separating hyperplane, and so basically, you see, we need the existence. So we need that there exists a continuous linear functional that separates it. So to have this, then it's enough to have this locally convex topological vector space, and to have this, that's enough to have this this topology, this is weak topology from the duality. So we're all good. And moreover, not only if we know that such a linear functional exists, by this previous results, we also know what it looks like. So we know that every continuous linear functional is of this form. So we get every continuous linear functional from the duality by just fixing one of the arguments to a suitable vector. Okay, so this is basically the key thing that we need. And okay, so then we can prove the so-called strong duality theorem. But before we do that, we just going to make some simplification. So we're going to require that the K2 cone is a zero cone. So before we had AX minus B belonging to the K2 cone. So if it's the K2 cone is just zero, then it's just this is just AX equal to B. So this is what we call usually the standard form of the conic linear optimization problem. And yeah, so then the dual cone K2 star is just the whole space. So this simplifies things. But interestingly, this is without loss of generality. It's a canonical situation because the previous problems that I showed you with all these 4 different spaces and the 4 different cones and the 2 dualities, this can be brought back to this canonical situation without loss of generality by a suitable transformation. The reason why I showed you the more general form is that it's sometimes useful, and in the second hour we will actually look at the problem where we need the more general form. But I think for many of us this is easier because we recognize this. If you are working in linear or semi-definite programming, you recognize this as a sort of standard form. We just have to interpret the duality and the cone in the right way. But I mean, everybody of us has seen some things like this before. And then the dual problem becomes that C minus A star L belongs to the cone K star. Okay, so now we no longer talk about K1 because K2 and K2 star are no longer interesting. So we just call K1 K. So now we have just one cone and K star in the dual for the dual cone. So it looks somewhat simpler. So for the strong duality, we ask ourselves, when is gamma equal to beta? And yeah, and then so here is the so-called strong duality theorem, or the zero duality gap theorem, as Darwin calls it. And so yeah, we have a condition that has to be met. So the condition that has to be met is that if this image, this is some linear image of the cone K. So the cone K, again, this is the cone we are optimizing in the primal problem now. And so we have to assume that this image, which has 2 parts. The first part is this operator A times X, where X is anything in the cone. And the second thing is the duality evaluated at X and C1, so the objective value at X in the cone. So if we look at this pair here, if this is a closed cone in the space E2 some R in the weak topology of the duality, then there is a primal feasible solution. Then the primal and dual optimal values gamma and beta are equal, and there is in fact a primal optimal solution. So this condition here is a sufficient condition for the gamma and the beta values to be equal, and providing that the primal problem is feasible, then this is also guarantees that there's actually a primal optimal solution. So I just want to show you just one picture just to explain the very, very high level idea about how this proof works with the separating hyperplane argument. So I just switch once more to the writing. So I just have a picture here for us to look at, and so basically this A hat K is some cone in a suitable space. Okay, so the elements of this A hat K, they have 2 parts. This AX part. So basically, yeah. So when AX is equal to B, then the linear constraints are satisfied. So we draw a line here where the first part of this 2-part argument is actually equal to B. So on this line, AX is equal to B on the red line. And then, yeah, so basically also we want for feasibility X in K So basically, we have to be inside this cone for feasibility. So everything in this red line segment here that I indicate now, this is in fact corresponds to feasible solutions. Okay, the second argument corresponds to the objective function value, which we are minimizing. So you see that, so in this picture, the minimum value for the second argument is just this value here, which corresponds to gamma. So I have here a point in the space where this cone lives, beta gamma, which corresponds to the optimal solution. So we cannot go lower in our minimization than gamma. So if we would go to gamma minus epsilon for some positive epsilon, then this would lie outside this cone. Okay, and then so we assume that this cone is closed. So now our separating hyperplane theorem tells us that there exists a suitable linear, continuous linear functional that separates this point here from this point here. Okay, and now the absolutely important issue is that we can describe the separating hyperplane in terms of a suitable linear functional. So basically, we can describe this linear functional in terms of a duality because we assume that we are working in the topology of a duality, and so this separating hyperplane, this continuous linear functional, is defined by some L in F2 and some sigma real number, and then basically the separating hyperplane just consists of the values y and tau, such that y L with respect to the duality 2 plus sigma times tau is some given value alpha. So every y and tau that satisfies this equality belongs to this hyperplane here. Okay, so it's very important. So we know that we can write our separating hyperplane in terms of a continuous linear functional, and we know that our continuous linear functional takes this form. And so then once you are at this point, then just the whole idea of the proof is proof that this L part is dual feasible. Okay, so the thing is that this L, you show that this L part is dual feasible, and then it will be its objective function value will be within epsilon of the gamma value. So you basically have this strong duality. And the existence of the optimal primal follows from the closeness here. So basically, you're guaranteed that this primal optimal solution is achieved as long as gamma is finite. Okay, so I think that is a good time to break because we have finished our hour and we still have another hour to go. So perhaps I just stop here and ask if there are some questions. So let me see if I can find the chat box. Okay, not too many questions. So that please just if you want to ask something, just unmute yourself and we can discuss. So then if there is nothing, let me just talk about the plan of action. So we reconvene at 11 a.m. and then I will just continue, and then we will just focus a little bit more on a specific case of the general problem of moments and its application to approximation theory. So and I will also, as I go along, I will give some exercises, and then for those who are interested in practicing a bit, we can look together at the exercises later this afternoon during the exercise session. Okay, so if there is nothing else, then perhaps we just postpone. We can have a coffee break and we reconvene at 11. So thank you very much, everybody.